Okay. Oh, by the way, I posted the YouTube video in YouTube for last lecture. Everybody can see it, right? There any problem accessing maybe the first class is not there. It's just syllabus. Probably you don't want to need to watch it, but later, okay, you may need to watch some of the class lecture again. So make sure it works on your Moodle. Okay, I basically posted a link of a YouTube video. Okay, and let me know if you couldn't see it. Okay, let me share my screen. That PowerPoint is for other class, but I want to pick some of the picture to show what is the fluid mechanics, right? So, okay, fluid flow. I pick this picture. Let me make a slideshow. Everybody see it? Do you imagine that actually when an aircraft take off, the flow is like this? Probably you know, right? Vortices, right? They generate a lot of vortex, but maybe not that significant, right? They put the smoke. They put some smoke when the aircraft, just a little tiny aircraft over there. You see that? Then when they take off, okay, wow, there are two vortices behind the wing, very big and very strong, very strong. Okay. So think about it. This is a tiny aircraft like this, right? What about a 787 jumbo jet? When it take off, what can it cause? What can it disturb the airflow? You will see. Imagine, you know, this is a small aircraft that's already very strong, very big vortex, although you cannot see it by naked eye, right? You cannot see it. The reason we put smoke is to make it visible. Okay, make it visible. So now we see, okay, the flow is like this. It's circulating, okay, generate gigantic vortices. Okay, so, okay, hold on. Let me turn on my waiting room. There are people waiting there. Well, so imagine that's it's a 787, 747. It caused a lot of, disturbance in the air. Okay, strong vortices, just like hurricane, right? Small scale hurricane, tornadoes, whatever. It's vortex. So then, if you are the small little ones behind that jumbo jet, what happens? You're waiting in the line to take off. There's the 787 in front of you. Okay, it take off. Can you immediately take off? Probably you can, but maybe it's not safe, right? You have strong vortices, behind you, behind the previous airplane. It's gonna suck you into the vortex. Okay. Oh, by the way, do you know? I said suck into the vortex, but do you know what I mean? Do you know the pressure inside a vortex is higher or lower? Do you know, by chance? I thought you're living in Louisiana. You experienced 2 hurricanes recently. Did you watch weather forecast?
Lower at the center of the vortex, I believe, right?
Yeah, the center of the vortex, is the pressure higher or lower?
It's lower.
It's lower, yeah, right? Everybody agree? Right, did you pay attention to that the weather forecast sometimes? Okay, when a hurricane comes, they talk about the pressure, center pressure. If it's low, it's dangerous. The lower it goes, the strong hurricane it is, right? So it's bad, right? So same thing here. This is a small scale hurricane, okay? And the center pressure is much lower than the atmospheric pressure, okay? Always, in the center of a vortex, the pressure is lower. Then what happens if you are taking off after the jumbo jet? Then you have a lower pressure area in front of you. Okay, maybe it's still safe, sometimes for the airplane, regular commercial airplane, to take off, but at least it will cause some disturbance. You probably will be forced into some of the low pressure region. Okay, so that's the fluid mechanics. That's an example of fluid dynamics, and you don't see it. the difficult part of fluid mechanics is in a lot of application, you can see clearly what happens. Okay, that's the major difference between fluid and solid. Solid mechanics, you always can see it. Well, it's a pendulum, it's moving, you calculate the velocity, acceleration, displacement, right? Those kind of things. I taught the 201, 202 before. But you always can see that object, okay, in solid mechanics. But in fluid mechanics, imagine without this smoke, colorful smoke, you don't even know what happens there. You can see nothing, you know, right? So that's the deal. But actually, although you cannot see it, but it actually, the motion of the fluid created tremendous amount of force, actually. In this case, low pressure means a suction force to the object behind it, okay? So that's what happens, okay? So that leads a question. It's difficult for us to learn fluid mechanics, right? You don't even see it, how you describe it. And if you don't know how to describe it, how do you calculate the force? Okay, so think about this. It's kind of a little bit more difficult than the solid mechanics to me. Okay, so what's our weapon? Your arsenal, you know, the weapon is mathematics, calculus. You're probably gonna rely on the math to tell you the truth, okay? Because you can see it, okay? So then that's the difficult part, right? Everybody hate math again, I guess. Okay, let me see. What's next picture? Okay, show you some more examples. Okay. Well, I think they are trying to do some wind tunnel tests here. Okay. They also put smoke there to show the flow. Okay. Flow over an object. They are the comparison here. Okay. It's a vehicle. Okay. The top picture. In the bottom is a block. Do you by chance educated the guess what's the purpose of this experiment? What they trying to measure or try to determine?
Drag.
Yes, that's a good educated guess. Drag, okay. This comparison is to show which one has better drag. I said better, I should say, which one has smaller drag. Drag is bad, right? If you're in the race car industry, you try to reduce the drag, minimize the drag, is that right? Always, I don't think drag is a good thing. Lift a different story. You know, in car, maybe you want a negative lift. Lift is not good. You're gonna flip it up. You wanna stick to the ground. So you want a negative lift. But drag, always bad. Okay, you wanna.
It's good when you want to slow down.
What?
It's good when you want to slow down.
Yeah, unless you want to slow down. But for the race car, I said race car industry, you want to be fast.
Well,
okay.
Until you have to turn a corner, then you can slow down.
Sure. So most of the time, you want to design a shape, you know, try to minimize the drag. Okay. So in this comparison, well, it's not a race car. It's just a regular car right here. But this is a block. Comparing between these two. Another educated guess. Do you think which one has a smaller drag?
The top one.
The top one, right? The car. Otherwise, why don't you make the car at the block? You know, you don't see sometimes you do. Some of the like a Honda Element, you know, it looks like a block. But most of the car is like this shape because that one has a smaller drag. Okay, but look at the smoke. Look at the flow structure illustrated by the smoke. Okay, does the drag actually related to the flow? That's actually my question here. By comparing this, you see two different flow patterns behind the object, right? Okay, so two flow patterns. This flow pattern on top actually leading to a smaller drag comparing to the bottom. Okay, you see, I feel it's not very clear, but still you can see the wake, the region, you know, behind the block, the vertical region, or I should say, like a vortices. Actually, there are a lot of vortices in there. Okay, the region, the wake actually for the block is bigger. Okay, the region behind the circulation region behind the car is smaller. Okay, that's an evidence. Okay, showing the flow pattern actually directly related to the force. You're engineers, right? Engineers try to, you know, do design, calculate the force. Okay, force is our goal, right? For all the kind of designs. So the flow, if you flow, it seems like there's smaller circulation regions, smaller wake in the car comparing to the block. And think about this. In vortex, the pressure is lower, right? Is the drag caused by the pressure difference between the front and the back? Right? In the front, if the high pressure, in the back has lower pressure, then you have a drag. The force, you know, the pressure difference push the car back, right? Is that right? Okay. So since there's a smaller circulation region, so you have a smaller pressure drop. The pressure is you know, it's lower for the larger circulation region. You have a larger vortex down there. You have a stronger hurricane. You have a lower pressure behind the block than behind the car. Okay, that makes sense? So in the front, the same pressure, right? The atmospheric pressure. There's no vortex, very few, a little bit vortex here, but comparing to the back is not much. Okay, so in the front is about the same atmospheric pressure, but in the back, the block has much lower pressure than the car. Okay, from that, I don't even need to put an instrument there to measure the drag. I can tell from looking at the flow that they have larger drag in the block. Okay. So that example shows you how flow related to the force. Okay. Okay. So if you can determine the flow, you can actually determine the force. Okay. In other words, if you can control the flow, you can control the force. Okay. See the big picture here? That's why fluid mechanics, basically a lot of application in the flow control. Okay. If you can control the flow, you can control the force. Okay. So these are a couple examples. Let me see what else in the slides. Yeah, another couple more examples showing the flow. See, that's a bigger airplane, right? When you take off, even when it's sometimes fly, changing slope, changing altitude, then you will see the vortex, very strong vortex. You can see it, right? So if you go across, you know, a cloud, probably you will see the vortex clearly from the cloud. Okay, but if it's clear sky, probably you cannot see anything. Okay. Okay, so this is just some examples. Let me, I don't want to finish all the, yeah. And, oh, okay, I can show you a couple more slides, you know. This one, the fighter jet, right? See those vortex structure? Okay. Educated the guests again, you know, look at this. This is the one. It's not a F-22, right? Like maybe F-16?
F-18.
Maybe F-18,
C.
you're right.
F-18C.
Okay, okay. Now look at this. This is the model, computer simulation, right? This is the actual picture, right? They have a common behavior of the vortex. You see the vortex? The two vortex streets on top of the wing, okay? Okay, so it's on top of the wing. So by educated guess, is this F-18 is taking off or landing?
Taken off.
Why it's taking off?
Because under acceleration, when you're taking off, you want the low pressure on top of the wing and high pressure on the bottom.
Exactly,
The
exactly.
aircraft is sucked up. That's how you have lift and flight.
That's the lift. The lift is the pressure difference between the bottom and the top of the wing, right? So bottom have nothing there, just normal, regular pressure, atmospheric pressure. In the top, you have vortex, strong vortices. Then you have low pressure. Just remember, vortex is associated with low pressure. So that's the taking off, lift, positive lift. Okay, so then when it's landing or going down, the vortex should be in the other side of the wing, okay, in the bottom of the wing. Okay, so the wing is actually a flow control device. Flow control, again, see, we control the flow, then we control the force. It's very smart, Wright brother invented airplane, right? Can fly heavier than air, aircraft, because they just utilize a very simple design, which is the wing. Okay, a wing can create the pressure difference, and create the lift, flow control. Okay. To study fluid mechanics, you have 3 different methods to study the fluid mechanics. Okay, the topic is very difficult. Okay, because it's hard to see, and it's basically solving a bunch of differential equations. Okay, it's very difficult. Okay, but we still have different ways to study it. Okay, theoretically, experimentally, as well as numerically. They call it the CFD, computational fluid dynamics. Okay, so well, in this class, engr311, obviously we're gonna do theoretical. It's a theory class, so we learn how to use equations to solve some fluid problem. Okay, but actually, in reality, only a handful of the problem can be accurately calculated, analytically calculated. Okay, only a handful of the problems. Most of the problem is too complicated to actually accurately calculate theoretically, because you can always use assumptions. You can assume the problem becomes simpler, then you apply equation to do it, to solve it. But those assumptions, these are the source of errors, right? You make too many assumptions, then the problem becomes a totally different problem. So it's not really representing the real situation. So if theoretical calculation is not good, then that leads you to experimentally do measurement, do experiment, right? We have class like a fluids lab, give you some taste of doing experiment to measure flow. So, and also the other way is numerically, you could use computer, okay? So-called computational fluid dynamics. What do you mean by computational fluid dynamics? Basically, those differential governing equation of the flow are the partial differential equations, conservation of momentum, energy, mass in the differential format, actually is non-solvable, okay? Non-solvable. So you can analytically solve it unless you make a lot of assumptions, okay? So become a ODE, then probably you can solve it. So what numerical CFD do is we actually use computer, not really solving the governing equation. We approximate the equation. We simplify the equation into a matrix, linear equations. The differential equations are not linear equations, but if we divide our domain into small elements, infinitely small, and we can assume on that infinitely small elements, the flow is linear. Okay, if it's linear, we can use the linear equation to represent the differential equation. Basically, that's the idea of CFD. We're not talking about CFD in this class, just give you some idea. Then if we break down those general differential equation into linear matrix, linear equation sets, then the computer can solve it. Okay, the computer, just like you guys probably not old enough to watch the movie, that Matrix movie. Well, no, that's very old, right? I watch it. You know, it's what 98. When I was in school, you know, it's pretty cool. At that time, I'm studying CFD. Okay, the world is a matrix. That's true, actually. We can simulate the world by solving a matrix. Okay, well, that's what it is. Okay, let me show you the equation. What does the actually flow equation looks like? It's terrible. It's very, very difficult. Navier-Stokes equations. Okay, so this is the fundamental governing equation for the flow. Actually, continuity equations, chapter 5, actually, we'll talk about the continuity equations. That's conservation of mass, okay? X, Y, Z momentum. Conservation momentum is a vector, so you have 3 equations for each direction, right? For the forces. Then conservation of energy. These are the differential form. Look at this. This equation is unsteady. Okay, I don't know. You already had the differential equation, right? Probably in that class, did you have this 301, math 301? At least some of you do, right? Okay, but you know a little bit about differential equation also in calculus, Cal 3, right?
Yes.
Yeah. So see, this kind of equation, probably it's not. This is not the first time you see those equations, right? You know, this is partial t, that means what? It's the time derivative. So these equations are not steady state. You know, it's changed with time. So what are the variables? You know, dependent variable are the UV, W. You know what UVW is? UVW are the velocity components, right? Velocity, you have UVW, 3 components. 3-dimensional, right? So it's 3D. You have UVW, you have X, Y, and Z, 3-dimensional. You have the time dimension, which is unsteady, okay? Then you also have a P. What is P? Stands for? P is pressure, right? You know, we're not directly solving the force, but it doesn't matter. Pressure, same thing, right? Pressure times area is the force. Then these are the shears. Shears you can break down into UVW velocities. Okay, so E is energy, right? So it's pretty complicated. It's this so-called Navier-Stokes equations. Navier-Stokes equation is this 5 equations. It's not just one equation. It's an equation set. It's the combine of the mass, momentum, of energy together. That's called Navier-Stokes equation, famous one. At least you had my class. You at least need to know this name, Navier-Stokes. Okay, 200 years. Okay, so famous one. Okay, flow. When we talk about flow equation, Navier-Stokes equations. Okay, unsolvable. It's nonlinear. Okay, nonlinear. You know, these are the partial rho UV, those partial rho VV. These are the nonlinear terms. So any nonlinear terms in a differential equation probably is a headache. Okay, it's non-solvable. So what's the strategy? What we can do? So it's not solvable. What we have in this class. So we will try to, you know, in this class, undergraduate fluid mechanics, not even directly try to solve these equations. Okay, we basically, how to say this? We basically use the solution of this. Okay, for example, Bernoulli equations. Bernoulli equation is a solution, basically. It's not really an equation. Come on, it's a solution from these Navier-Stokes equation. So we use those solutions to solve practical problems. Okay, that's actually the goal for this undergraduate fluid mechanics class. For graduate level, we actually attempt to solve the Navier-Stokes equations. Okay, but for undergraduate, probably don't worry about solving it. we need to just use the solution to solve. You know, the differential equation, the solution for the differential equation is the equation, right? Okay, so but if you want to solve this Navier-Stokes equation, you have to make a huge amount of assumptions to get rid of some of the terms in this equation. Assume they are zero. Okay, so then it becomes simplified form of this equation, then possibly become ordinary differential equations, and with less dimension, maybe 1D or 2D, maybe you can solve it. Okay, so that's the story behind this fluid mechanics experiment. We can go through this a little bit more. Experiment, you have to measure, right? So what we really measure, we measure velocities. Okay, velocities, because so the fundamental question is what's the meaning of, what do you mean by dynamics? This is fluid dynamics, right? You know fluids, right? But what really means dynamics? It's a subject, right? It's a science or a topic to study the relation between speed and the force, velocity and the force. Okay, anything moves, they have consequences. It has consequences. Everything moves, it has consequences. Okay, the consequence is force. Okay, so everything move, it will lead to a force, or vice versa. You apply a force to something, it will start to move. Okay, you see that relation? Movement and the force. Okay, dynamics is a topic to study this relationship, movement and the force. Think about yours 202, solid dynamics. Movement, pendulum moves, force. Okay, there's always a relation between them. So if you can determine the velocity, maybe there's some relationship. You can use some equation to calculate the force. That's dynamics. Or you know the force you apply to the system, then you can predict the velocity of the system. Okay, so that's dynamics. So fluid dynamics, so in that sense, what we want to know is, in fluid mechanics, fluid dynamics, the difficult part is the flow, because it's invisible. Okay, so without knowing the flow, without knowing the velocity accelerations, there's no way you can find out the force. Okay, so the major part of the experimental fluid mechanics is to determine the velocity field. Okay, determine the velocity field. Think about that. I use the word field. Okay, like a Star Wars force field. Velocity field. Okay, so it's a space you're talking about. Okay, yeah, a volume, a space, and the velocity is changing in that space. Okay, the velocity is change everywhere, just like the airplane example, the first picture I showed you. Okay, it's a circulation, it's a vortex, right? Smoke show the vortex. So in that space, the velocity everywhere is different. Right? Think about this. Velocity is what? It's speed plus the direction, right? Is the velocity the vector? Right? In that space with that circulation. Okay. Velocity changes everywhere in that space. Okay. The direction, think about this circulation counterclockwise. Okay. So the velocity, of course, the speed is different. Every layer of the circulation, the speed is different. Speed means the magnitude, right? But the direction, look at the direction. Everywhere the direction is changing, is different. Okay, so the velocity, you know, is fully non-uniform. Okay, it's changing everywhere. So if you want to measure the velocity in this space, well, it becomes terrible job, terrible task. It's very difficult. Okay, to exactly identify the magnitude and the direction. So how to do that? It's difficult. Yeah, it's not the topic of this class, but they have very expensive equipment, you know, try to measure velocity. This is the PIV, right? Particle image velocimeter. So they can measure velocity, use lasers, you know, small particles, dust particles in the air. Okay, it moves, then it reflects lights. Okay, so dust. Okay, they sometimes inject particles in the flow. So then those lights, then the laser can reflect the laser lights, those particles. So you can actually track the movement of those small particles on different times, track the, take pictures. Okay, if you can track a particle, you take picture at 2 different times, you know the location, how the location change of the particle, same particle, then you can calculate the distance, speed, then the velocity, acceleration, those kind of things. Okay, so it's very expensive, very, you know, very expensive and complicated. This is what, this is the wind tunnel, right? You see, you put an aircraft there. It's a fancy aircraft in a wind tunnel, you know. This is probably Langley, Virginia, NASA Langley, one of the largest wind tunnel in the world. Okay, so see, such a big space, you know, just for a wind tunnel. Okay, so how big it is. It's very expensive to do the measurements. Okay, so anyway, I guess the CFD part I'd probably show you later. Okay, so let me turn off this. Okay, this is just a quick review of what is fluid dynamics. Okay, so how to study it. Okay, let me turn on I have a whiteboard here. I need to write something. Okay, here it is. Can you see it? The whiteboard? Okay, good. Let me write something on it to see. Okay, I have a question here. I talk about the, okay. So I think in the textbook, the first question in the textbook it wrote down, it writes is, so what is fluid? Okay, so okay, I already show you a lot of pictures. Okay, what fluid look like. Okay, so but how to, you know, define it? Fluid. This is a fluid is a kind of like a matter, right? Material, matter, or medium, whatever. Okay, it actually moves. To me, it's just basically it moves. Is that right? But you should say, hey, solid moves too. You know, you have a pendulum, a car, it moves. But so how to describe it? In the textbook, you use a sentence to say describe fluid is continue to deform. Fluid, you know, continue to deform under the action of a shear stress. You don't need to write notes. I will post the PDF of my notes on Moodle. Okay, so it's just look at the screen and listen. Continue to deform under the action of a shear stress. Does that make sense? Under the action of shear stress. Shear stress is a, you know, it's a force per area, right? Representing a force. So you have to have a force. Okay, this sentence, I just want to translate this sentence. Under action of force, shear force, shear stress, okay, and continue to deform. Does that make sense? Deform. Deform means changing shape, right? So I said pendulum. Pendulum moves. Okay, is pendulum a fluid? From this definition, well, you can add a shear stress to the pendulum. Sure, your normal force or shear force, whatever force you're adding to it. Okay, that's fine. Then it moves, but does it deform? No, it's not deforming. You know, it moves. Basically, you push it, but the material itself doesn't deform, doesn't change shape. Okay, then it's a solid. But now it's here. If it changes shapes under a tiny little bit of shear stress, it deforms, then it becomes fluid. Does that make sense? Think about your open your faucet, a water stream coming out. Okay, water stream coming out of your faucet. Okay. Use your hand knife, hand sword. Can you cut through the water stream? Okay, think about the hand sword, just like a scissor. If you have two hands, basically it's a scissor, right? It doesn't matter, one hand, you can also create a shear. Okay, you go through, the hand sword goes through the water stream. Okay, you actually apply shear stress to this water, okay, to the water stream. And what happened to the water? When your hand try to cross it, touched it, keep going, the water go around your hand? Okay, so the water deforms, change the shape. Okay, it's so easy to change shape. During the shape changing, the velocity changes. Okay, so that's what the definition is. Okay, so think about all the fluid. You know, it will continue to deform under the action of the shear stress. Okay. So, but I want to emphasize this is not really, it's not a clean cut between fluid and solid. No matter what kind of definition you use, if you Google it, what's the definition of fluid? Hey, maybe you can have tens of different definitions there. Okay. It's not very clean cut. Okay, very clean cut between fluid and solid. I give you an example. If you Google glass fluid, have you ever heard about the glass is a fluid? If you Google glass fluid, you will see many people believe glass is a fluid. Why is that? I don't know if you ever been to old church, like in Europe, a lot of church 200, 300 years old, you know, they have some antique glasses sitting on there for hundreds of years. Okay, you will see actually the bottom of the glass is thicker than the top of the glass. Okay, it's thicker. Why thicker? When they build it, it's not thicker. It should be this uniform thickness. Because years, you know, glass gradually moves down, flows down due to the gravity. You know, look at the definition here. Continues to deform under the action of the shear stress. Okay, so gravity acts as a shear stress in this case, right? See the parallel to the glass wall. Okay, so it's a shear stress. Okay, so then the glass deforms, although it takes hundreds of years. But hey, if I Don't care about time. It actually moves. It actually deforms. So your definition is not that. Is glass really a fluid? Well, some people believe it is. Some people don't. Okay, if you go Google that topic, you definitely will see different arguments. Okay, based on the different definition of fluids and solid. Okay, so this is one of the definition I like, because that related to the directly related to the force and the movement, right? The deformation. So, but there's other definitions of between, you know, glass and the fluid, between solid and fluid. If you look at the molecule level, okay, small scale. Molecule level. So they say solid is molecule ordered. It's the structure is ordered, and the shape is the rigid inbound. At least that's one definition I can see. Okay, the molecule ordered, molecular structure, and for fluid, the molecular structure is disordered and not rigid inbound. Okay, that's I can find another one. You know, if you Google the definition of fluid, you can find different ones. Different people define different ways. But look at this. So then this definition is not good either for glass. Okay, glass actually, if you look into the glass molecules, they are actually not ordered. They are very disordered, disoriented, the molecules. It doesn't have a formed structure, okay? But it's rigid inbound. This both basically looks like a rigid inbound. So based on this definition, the glass is not fluid and not solid either. Okay, so I use this example just try to show you that the definition is relative. It's not a very clean cut between fluid and solid. There's always something in between. Okay, so that's fluid dynamics. So we talked about, right? Of course, statics is easy. Fluid statics basically is not in motion. You have force balance, just like engr311, right? So force balance equal to 0. That's it. When you talk about dynamics, you introduce the motion. So you introduce the velocity. So dynamics is the relation between the movement and the force. Everything move cause a force, especially when the movement changed. You will have a very obvious force result from the changing of the movement. Okay, for example, you drive a car.
Professor.
Yes.
What is that word or figure to the right above dynamics? Is that a word or is that like a concept?
Not rigid inbound, I think. Is that what you talk about?
Oh, that's what it said. My fault. I didn't even know what it said.
Yeah, I'm sorry, my writing. You know, one is rigid inbound, but the solid one is not rigid inbound. These are the different classifications. So for fluids, sometimes you know, you don't have to agree with them. You know, some always have some exceptions. Okay. Dynamics between force and the velocity movement, right? So for example, you drive a F-150, 60 miles per hour on 210. You hit the pole, light bulb, boom. What happened to the speed? 60 miles per hour suddenly goes to 0 miles per hour. Okay, stopped, crashed. What happened to you? Something bad happened to you, I guess. If you stop from 60 miles per hour to 0, you know, you could die. You know, you could get injured. What caused the injury? It's a
Your
force.
Banging
momentum.
into it.
Yeah, it's a force. It's anything damage you, it's the force. Okay, so what causes the force is the speed change, acceleration, deceleration, whatever, right? But the direct reason to cause injury is the force, impact force. Okay, impact force, then you get hurt. Okay, but the force is coming from the sudden change of the velocity. So that's the example, right? Conservation momentum, basically F equals to ma. You have an acceleration, you have a mass, right? If we talk about dynamics, you always want to use this equation to start with. Is that right? Newton's what? Which law? First or second or third? Yeah, Devin's right. Second law, right? Newton's second law. Force equals to mass times acceleration. Okay, so your F-150, huge amount of mass. Acceleration when you crash, 60 mile per hour to 0 mile per hour in like 1/10 of a second. So you can calculate that acceleration pretty big. Deceleration, right? So then mass times acceleration is a force that could kill you, right? That's a force injury you. So conservation momentum, right? In dynamics, that's the most important principles. Here in fluid mechanics, fluid dynamics, same thing. Also most important principles. So let me ask you a question. Is a small car safer or big car safer? Well, we're engineers, right? We apply the science and technology into real-time problems. Can you answer that question?
Wouldn't it be big because they have more like to keep you? Like it has
Look
more
at the
mass.
equation.
The big one has more energy, more bigger force, but you also have more space for safety features like crumple zones, airbags, those sorts of things to try to cancel out that ground force.
Right.
So it depends on the
Right.
exact cars in question, for being honest. But the big one has more force, small one has less force.
Both of you have a smart answer to this. Depends. Both of you, you try to say it depends. It's not 100%, not absolute. So don't get fooled by those commercials, ads that say, hey, it's safer or whatever. You're engineer. You're smarter than most of the people. You know, you need to think. It depends. Okay. Indeed, when you hit a tree, when you hit a stationary object, okay, then you stopped. You have a deceleration. You have your mass. So the force. I'm not talking about how safe the structure is. I'm talking about how much force you will experience. Sure, bigger car will experience bigger impact force, no doubt, when you hit a stationary object. Okay, so you will have, for example, MA, right? A is the same, small car and bigger car. Mass, bigger car could double the mass of the small car. So your impact force is 2 times, okay? But think about this. They say actually, the reason they claim small cars safer is they say, hey, more than 50% of the accident, fatality, is caused by the accident that car hitting a stationary object, like a tree, a wall, or something like that. Okay, so they say, hey, when you hit a stationary object, okay, small cars safer. Okay. But see, the question is, okay, I'm sober, I'm not drinking, you know, I'm not gonna hitting a stationary object myself, and I'm pretty confident on that, okay? I'm not confident is somebody drunk hitting me when I'm driving my car on the highway, okay? So in that sense, okay, think about this. When 2 cars collides, let's say a bigger one, a tiny little one, they both has momentum. Okay, when they hit together, what happens? Okay, mathematically, so you know it's safer for the bigger car hitting a small car. You know it's safe, common sense, right? That's a word we're using. But mathematically, we can prove it because you have, when you hit together, you have 2 momentum. You're hitting together, 2 force adding to each other. So the overall force will be your F1 plus F2. That's the overall force the two people both experienced when they crash. That makes sense? So you're considering the overall force, not the one force the small car create. No, your overall force. So the F1 is from the bigger car, F2 is from the small car. The overall force, of course, you're hitting a giant car, you experience the other car's force also. So the overall force, the two people share the same. So in that situation, the small car, of course, is less strong than the bigger car. Okay, it's bad. You know, it's good that everybody drives small car, but that's not possible, right? So, so in this situation, although they claim it's, you know, for some economic purpose, they always want to claim that more than half of the fatality is from accident the car hitting non-moving objects. Okay, but when you have accident with moving objects, then the story is totally different. Then in this situation, bigger car is safer, obviously. Okay, so I guess, see, that makes sense? I just like to always relate it to math and science to the reality, real life. So that's also in this class, that's what we try to do. Okay, fluid dynamics. I guess that's the, any questions so far? Jump in, if you have any question, let's talk about it and discuss in class. Okay. Let's do the flow classification. Next stop. Flow classifications. Okay. The first one I want to introduce here is something called hydrodynamics versus gas dynamics. Okay, combine these two are fluid dynamics. Both water, liquid, and the gas are fluid, right? Do you agree? Both of them are fluid. Should be they are pretty light and they continue to deform under the action of shear stress. So they both classify as fluid. So hydrodynamics means the liquid, right? Most of the time we talk about hydrodynamics like what, water or something, liquid. Okay, and the gas dynamics means gas, right? So what's the difference between them? I think the difference between them is the density. In one case, density changes easily. In one case, density doesn't change that much. Okay, which is which? You know, of course, this doesn't change, and this does change. Gas dynamics, you have thermal, right? I think everybody should have thermal, reach to when you reach to here, to this point. Thermal, it's all talk about the density change in the gas. You pressurize it, temperature change, density change, volume change, right? So for gas, it's easy to pressurize and change volume, change density, okay? But how about liquid? Can you pressurize water? Wow, I shouldn't ask, can you? You always can, you know, nothing you cannot, but it's not easy, right? So it's really, the density, even under tremendous amount of pressure, the density won't change much, slightly maybe for the water. But for air, hey, you pressurize a little bit, your temperature increase a little bit, density increase, right? So that's a difference. So in this class, we focus on this. Your life is much easier with this because density is a constant. Okay, do you remember that slide I showed you, that governing equation? The partial differential Navier-Stokes equation. Density is actually in the numerator. It is a dependent variable if it changes. Okay, so you basically introduce one more variables into the equation. It'll make life a little bit more difficult. Okay, now here, if you treat density as a constant, you can easily move the constant outside of the derivative. Okay, become a constant. So your equation is much simple. Okay, that's why for the gas dynamics, okay, you have to use the energy equation combined with the momentum equation. But because you have one more variable, density, right? You have to use the energy equation, temperature. But for the hydrodynamics, for the liquid, you don't have to use. You can just simply use momentum and mass equation together because you have one less variable. You require one less equation. Okay. Okay. Let's turn to next page. So similarly, we said hydrodynamics and the gas dynamics. Now, similarly, we can call them incompressible fluid and the compressible fluid. Okay, incompressible versus compressible fluid. Okay, from the name, it's pretty self-explanatory, right? Incompressible, it's not easy to compress. So density is a constant, rho is constant, rho is not constant in the problem. Okay, for the compressible fluid. Again, this is incompressible fluid is our topic here in engr311. We still deal with gas, deal with air in some of the problem in this class. But for those problems, when we deal with air, the density of air doesn't change. Okay, we assume it doesn't change. The density doesn't change, then it still can be classified as incompressible fluid, although it's air or gas. Okay, that makes sense? So we can still deal with the air problem or gas problem, okay, as long as the density doesn't change. As long as it's not under a tremendous amount of pressure. Yes. Any question? I heard somebody talking. Okay. So this is the one classification. I think we have a elective class called gas dynamics. Remember for ME, for mechanicals. Okay. So if you're interested in continuing learning fluid mechanics for the compressible flow, that's Dr. Chandra's expertise. He will teach that class. Okay. Another classification. It's very important. You guys need to know. Uniform flow versus non-uniform flow. Okay. Uniform flow versus non-uniform. So that related to a fundamental difference between fluid mechanics and solid mechanics. Okay. Solid mechanics, what is your object? Well, if you have a car, if you have a pendulum, you clearly know what is your object. It's the car, it's the pendulum, right? So in solid mechanics, uniform and non-uniform speed, that's easy. Just look at that object. Is it move with the constant speed? Okay. So it's clear object, okay. But in fluid mechanics, what is the object? That's a fundamental question here. Okay. Daniel, I see you. You are the first one on my screen, okay. So you're sitting in a room, nice, comfortable room, okay. If your air conditioner is on, okay, so there's actually airflow around you, okay. So you sitting in this room with airflow on, what is the object of the flow of this problem?
Would it be me disturbing the airflow?
If we study fluid mechanics, okay, for your room, your object is actually, how to say this? Either the airflow, is the airflow your object? Yeah, that's the question.
Yeah.
Seems like airflow is your object.
It sounds like a trick.
Yeah, it's like a trick. Yeah, yes, it is. It's okay. Let me answer myself. Airflow going around you, right? You have air coming out from your vent, okay? You have probably 3 trillion particles in 1 minute. air particles go out of the vent, go through the space, and go to you. Okay, and they go around it and circulate the room. Some leak out of the room, something like that. Okay, so I'm telling you, it's not possible to study that 3 trillion particles altogether. Okay, each particle has its own motion. Okay, one way to study is, hey, we apply the solid mechanics principles. For example, each particle is like a pendulum or ball. Okay, we track the movement of that particle or ball. Okay, so altogether we can see the relative picture of what the flow look like. Okay, that's one way, but is that possible? Well, at least not possible now. I don't know in the future, quantum computing, that may be possible. When I do my PhD, that's actually a group member of mine. We are in the same group. They develop a method called molecular dynamics for fluid dynamics. They actually track the particles, but not 3 trillion. They track probably 3,000. Okay, to represent the what particles or similar particle around it. Then they track 3,000 particles. That's reasonable. Okay, they can every time step they can calculate each of the 3,000 particles. Maybe 30,000 is okay either. Maybe 3 million is even okay nowadays. Computer is powerful. Okay, then statistically they can find the statistical figures of what the flow look like in every time step, every moment. That's one way to study, but not this class. Yeah, we're not so advanced here, okay, to reach to that level. Okay, so Navier and Stokes, early times, they developed a method to study the fluid mechanics is not to look at each individual particle. We never look at the particles. Instead, we look at the space. We study the space that affected by those particles. So what kind of air movement, what kind of speed as you sitting there experience? That's actually what we interested, right? I don't care about the particle, 2 trillion, 500 billion, or I don't care about that particular particle. I just care, hey, I'm sitting in the room, how comfortable am I? Especially for engineer, we serve a purpose, right? We're not serve purpose for that particle. We serve purpose for ourselves. Okay, for human being, do you feel comfortable? So our goal is, instead of studying the individual particles using the solid mechanics method, we totally get rid of that method. Instead, we look at the space. Use the space as our object. See, hey, how the space is affected by those particles. Okay, in that sense, if you want to measure your airflow in your room, okay, I have 1,000 velocity meters. I have 1,000 sensors. I place that 1,000 sensors evenly distributed inside your room. Each sensor will measure a velocity on that particular location. Okay, get the information of all these 1,000 sensors. I have a clear picture what's the airflow look like in your room. Okay, so that's the way we do experiment. That's also the way we do theoretically calculate the fluid mechanics. Instead, we're not looking at the particle, we look at the space. We divide the space into every location. Let's see what's the velocity over there. Okay, so that's the fundamental difference between solid and fluids. Okay, so come back to this classification: non-uniform flow and the uniform flow. Okay, so in terms of the space you're looking at, so your object is the space. It's not the air particle itself. Please remember this. This is the fundamental difference. Okay, so now I'll come back to this question. Daniel, I understand I'm picking on you. I'm sorry, you're in the first image here. Okay, so in your room, if the AC is on, okay, is the flow in your room uniform or non-uniform?
Non-uniform? I would think you'd lose velocity further from the vent or something like that, or just as the pressure decreases as it fills more space.
So go back to my example. I said I put 1,000 sensors in your room. Right? evenly distributed in your room, 1,000 velocity sensor. Okay. Do you think at any given moment they will measure the same velocity or 1,000 sensors?
Probably not.
No, no way. Definitely not. Not that easy to get the uniform flow. If the sensor get different readings, it's non-uniform flow in terms of a target space.
But it would be uniform coming out the air handler, right?
Depend on how you define the space, which space you're looking at. You see,
I was thinking
for the
that
question here, you have to go back to the question asked to yourself, what is the space you're looking at? That's our object. If you look at the immediately outside the vent outlet, maybe they're kind of relatively uniform. Okay, I just really hate to use absolute uniform, those kind of words. It's always relative. It really depends on the space you're looking at. Okay, if you're looking at the whole room, no way it being uniform. Okay, so in terms of space, uniform and non-uniform. Okay, constant speed. Velocity is constant inside the space. And the velocity is non-constant inside the space, target space. Then it's non-uniform. Okay, does that make sense? Remember this 1,000 velocity sensor example. I will give it to you. It's very, very easy to understand then. Because now I'm gonna introduce how many minutes I have. I have 4 minutes, okay? Let me introduce the next one to confuse you. Unsteady flow versus steady state flow. Okay. Now, you have 1,000 sensors in the room, okay? Every sensor get different readings. But if I check every sensor, each sensor, okay? I check the sensor 8 o'clock, 5 meters per second, okay? Sensor number 2, 5 meters per second, okay? I check the sensor at 9 o'clock, 5 meters per second. I check the same sensor number 2, 2 o'clock in the afternoon, 5 meters per second. Okay, I don't care about the other 999 sensors. On this particular location of sensor number 2, the velocity doesn't change with time. Okay, at least on that location, it's steady. Okay, so this is totally independent question comparing to this, okay? Uniform and non-uniform doesn't care about the steady or unsteady, doesn't care about the time. Here, steady or unsteady, doesn't care about other locations, just talk about any given location. Okay, so in that sense, I check every sensor. Okay, number 2, number 3, number 1, number 999, all the sensor. The reading, although they are all different, but the reading always doesn't change with time. 8 o'clock, 9 o'clock, 2 o'clock in the afternoon, every sensor gets the same reading. Okay, same reading, although they are different. Okay. So on every location, they are steady state, although the whole thing is non-uniform. It's a non-uniform steady state flow. Okay, very confusing here, very confused here, okay? So in terms of time, in terms of space, okay? It is all the combination possible. You can have unsteady state uniform flow. You can have non-uniform unsteady state. You can have non-uniform steady state. You can have steady state uniform. Think about it. I'm out of time here. I'm continuing on this next time, but think about it. Can you have a example in your mind to represent each of the combination? There's 4 combinations here. Okay, yeah. Think about it. I'm out of time today. Let's talk about it next Tuesday. Okay. Hope it's not too bad. The first class of mechanics. Have to put on give you any question. Homework problem yet? No math yet. So it seems like it's okay. Later on will be terrible. Okay. Okay. Let's stop here. Okay. Have a good weekend. It's Thursday, and then no homework this week. So see you next Tuesday. Okay.